The Earth, our blue planet teeming with life, is the result of an extraordinary sequence of events in cosmic history. It emerged from chaos, a product of stellar death and rebirth, and evolved over billions of years into the vibrant world we know today. The story of Earth's birth and its early evolution is a tale of fire and water, of collisions and cooling, and of the mysterious origins of life itself. Understanding the first two eons of Earth's history, the Hadean and Archean, requires us to look back over 4.5 billion years, to a time when the solar system was young and violent, and Earth was an unrecognizable, molten inferno. These eons are the foundation of our planet's development, encompassing its fiery formation, the establishment of its first solid crust, the formation of oceans, and the emergence of the earliest forms of life. In this essay, we will dive deep into the geological, astronomical, and biological processes that define the Hadean and Archean eons, exploring the science behind these epochs while appreciating the sheer wonder of Earth's transformation. Along the way, we'll discover astounding facts that underscore the miraculous nature of our planet's evolution. To understand Earth's beginnings, we must first explore the birth of the solar system. Approximately 4.6 billion years ago, a giant molecular cloud composed of gas and dust began to collapse under its own gravity. This collapse was likely triggered by the shockwave from a nearby supernova, a massive star exploding in its death throes. As the cloud contracted, it spun faster, flattening into a disk-like structure known as the protoplanetary disk. At its center, the intense gravitational pressure and heat led to the birth of the Sun, a glowing nuclear furnace. Surrounding the Sun, the remaining material in the disk began to coalesce into solid particles, which collided and stuck together, forming planetesimals, the building blocks of planets. Through a process called accretion, these planetesimals grew in size, colliding to form larger bodies known as protoplanets. One of these protoplanets would become Earth. The Earth that formed during this period bore little resemblance to the planet we know today. It was a molten sphere of rock and metal, its surface a fiery ocean of magma. This tumultuous period, lasting from Earth's formation until about 4 billion years ago, is known as the Hadean Eon, a name derived from Hades, the Greek god of the underworld. Several key processes shaped Earth during the Hadean Eon. 1. Differentiation of the planet. As Earth grew larger, the immense heat generated by accretion, radioactive decay, and gravitational compression caused the planet to melt. In this molten state, heavier elements such as iron and nickel sank towards the center, forming Earth's metallic core, while lighter silicate materials rose to form the mantle and crust. This process of differentiation gave Earth its layered structure. 2. The formation of the Moon. Around 4.5 billion years ago, a cataclysmic collision occurred between proto-Earth and a Mars-sized body named Theia. This impact ejected a massive amount of debris into orbit around Earth. Over time, this debris coalesced to form the Moon. The Moon's formation had profound implications for Earth. It stabilized the planet's axial tilt, preventing extreme climate swings, and its gravitational influence created tidal forces that would later play a role in the evolution of life. 3. Volcanic outgassing and the proto-atmosphere. In its early years, Earth had no stable atmosphere. The hydrogen and helium that surrounded the planet initially were stripped away by the solar wind. Volcanic eruptions released gases such as carbon dioxide, water vapor, methane, and ammonia, creating a thick, toxic proto-atmosphere. 4. The heavy bombardment. The Hadean Eon was marked by a period of intense asteroid and comet impacts, known as the Late Heavy Bombardment, which occurred around 4.1 to 3.8 billion years ago. These impacts delivered water and organic molecules to Earth, playing a crucial role in setting the stage for life. By the beginning of the Archean Eon, Earth had cooled enough for a solid crust to form. However, this crust was far from stable. Intense volcanic activity continued, with magma flows and tectonic movements shaping the surface. The first continental landmasses, known as cratons, began to form as lighter granitic rocks accumulated and rose above the molten mantle. The Archean crust was vastly different from modern continents. It was thinner, more fragmented, and continuously recycled through subduction and volcanic eruptions. These early landmasses served as the foundations for the continents we see today. One of the most transformative events during the Archean Eon was the formation of Earth's oceans. Water vapor, released by volcanic outgassing, condensed as the planet cooled, falling as rain and filling the low-lying basins. By around 3.8 billion years ago, Earth was covered by vast oceans, albeit ones far different from the modern seas. These early oceans were acidic and rich in dissolved minerals such as iron and silica. They provided the perfect environment for complex chemical reactions, potentially leading to the origin of life. The great mystery of life's beginnings. The Archean Eon marks the dawn of life on Earth. The exact process by which life emerged is still unknown, but several hypotheses attempt to explain this profound event. 1. The primordial soup hypothesis. Life may have arisen in Earth's oceans, where a soup of organic molecules formed through chemical reactions driven by lightning, ultraviolet light, and volcanic activity. These molecules eventually assembled into self-replicating entities, the precursors to life. 2. The hydrothermal vent hypothesis. Deep-sea hydrothermal vents, where mineral-rich water and heat create unique chemical environments, may have been the cradle of life. These vents provide energy and nutrients, making them ideal for the synthesis of organic molecules. 3. The panspermia hypothesis. Some scientists propose that life's building blocks were delivered to Earth by meteorites or comets, a theory known as panspermia. This idea suggests that life, or at least its precursors, could exist elsewhere in the universe, the first life forms. The earliest evidence of life comes from stromatolites, fossilized structures created by colonies of cyanobacteria. These microorganisms, which appeared around 3.5 billion years ago, were capable of photosynthesis, a process that uses sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. Cyanobacteria played a crucial role in transforming Earth's environment. Their photosynthetic activity began to introduce oxygen into the oceans and atmosphere, setting the stage for the eventual rise of more complex life. Tectonic activity and crustal recycling. During the Archean Eon, tectonic activity was vastly different from what we observe today. Plate tectonics were in their infancy and the crust was thinner and more dynamic. Volcanic activity was rampant, recycling the crust and releasing gases that contributed to the atmosphere. The interaction between the early atmosphere, hydrosphere, and lithosphere created feedback loops that influenced Earth's evolution. The atmosphere transformed. The Archean atmosphere was still dominated by methane, carbon dioxide, and nitrogen, with little to no oxygen. However, the activity of cyanobacteria slowly introduced oxygen, which initially reacted with dissolved iron in the oceans, forming iron oxide deposits. This process led to the formation of banded iron formations, which are some of the oldest sedimentary rocks on Earth. 1. Ancient rocks, the Acasta gneiss in Canada and the Jack Hill zircons in Australia, provide some of the oldest geological evidence of Earth's crust, dating back over 4 billion years. 2. The Moon's influence. During the Hadean, the Moon was much closer to Earth, creating massive tides that could have driven the mixing of chemicals in tidal pools, aiding the origin of life. 3. Life's resilience. Early microorganisms thrived in extreme environments, such as deep-sea vents and boiling hot springs, demonstrating the incredible adaptability of life. 4. The rare Earth hypothesis. The combination of events that allowed Earth to develop life is so unique that it may be exceedingly rare in the universe. The Hadean and Archean eons are chapters of Earth's history that highlight the planet's incredible transformation from a fiery, lifeless orb to a world capable of supporting life. These epochs remind us of the delicate interplay of astronomical forces, geological processes, and the mysterious spark of biology that led to our existence. As we study these ancient times, we not only uncover the origins of our world, but also gain insight into the potential for life elsewhere in the universe. Earth's early evolution is a testament to the profound and wondrous forces at work in the cosmos, shaping planets and paving the way for life to emerge against all odds.